So any of these methods can increase the efficiency, but any of these methods have some limitations or can cause some issues or difficulties in the cycle itself. This is why we think of a new method, which is ideal reheat Rankine cycle. This is one of the methods, one of the modifications that we did to a Rankine cycle, and this method helps us to avoid the limitation that we set for each of the previous methods. What is this reheat Rankine cycle? This is the TS diagram for Rankine cycle. Clear? We have 4 points, 1, 2 for the pump, 2, 3 for the boiler, 3, 4 turbine, 4, 1, 2 the condenser. So we have here, let me write these names. So this one, what is happening inside the pump? 2, 3, this representing the changes happening inside the boiler. 3, 4, this represents what is happening inside the turbine. And 4, 1, the last one, this is what is happening inside the condenser. For the ideal reheat Rankine cycle, this is the TS diagram. Okay. Just take a look and tell me what you can, or how can we describe the differences between here? What is happening? Anyone can describe what is happening? Let's start step by step. For step 1, 2 in the pump, do you see any changes in this step? So the pump will be the same. Okay, we have here step 1, 2. This is still the pump. Here in the condenser, we have 4, 1. Here this is 1 representing the condenser. So it's almost the same. We have a horizontal line in the area under this curve. So this will be the same. So we still have pump, we still have condenser. No difference has happened between the Rankine cycle and reheat Rankine cycle. From point number 2 to point number 3, this represents the boiler, right? So we still here have the boiler. Here, the outlet of the boiler goes to the turbine and we have expansion. Here we have the outlet of the boiler goes down. As long as it goes down isentropic, this means we have an expansion happening inside the turbine, right? But the expansion is not going to the lowest pressure we have. We have like expansion up to this point. So here we have turbine and we have expansion happening. But we don't complete to the condenser pressure. We don't come here. We stop at a certain point, point number 4, and then what is happening to the line? The temperature start to increase again. So we have a reheating happening. So we have temperature increase one more time and to a certain point, and then once we reach this point, we have like isentropic expansion happening. Isentropic expansion happening, so this means we have another turbine. See the change we have here in the TS diagram, so we have difference happening, so we don't have a single step expansion happening. The outlet of the boiler is not subjected to single expansion directly to the condenser pressure. It's expanded to like a certain pressure value, then we reheat it again. Then we expand it again. So how many turbines we are using in this one? 2 turbines. So the change here we are using 2 turbines. Plus we have intermediate reheat step added. So we add a turbine to the system and we have a reheating step. Okay, plus the boiler. So we have boiler, heat addition in the boiler, plus reheat, this one. So let's see the components. This is the Rankine cycle, the conventional one. We have pump, boiler, turbine, condenser, the fluid is moving in this one. And this is what we have in the reheat Rankine cycle. So what we have in the reheat Rankine cycle, we have high pressure turbine, we have low pressure turbine. We have 2 turbines. We have stream from the pump, will go to the boiler, it's reheated. This point number 3 will go to the high pressure turbine. But after the turbine, it will not go to the condenser. It will go back to what? To the boiler again. So we have 2 heating steps happening. we have two expansion steps happening. The outlet of the first turbine will not go to the condenser, it will return to the boiler for reheating, and then the outlets of this one will not go to the high pressure turbine again, it will go to the low pressure turbine, and the outlet of this turbine will go to the condenser. Okay. So the outlet of the boiler will go to the high pressure turbine. Then it will exit the turbine, return back to the boiler. We have reheat happening for this stream, and then it will exit to the lower pressure turbine, and from the lower pressure turbine it will go to the condenser. Okay. So we have this part is representing an extra part like happening here. We don't have this part in the original cycle. Originally what we have point number 3, go to the turbine and then go directly. This is the original cycle. So this is the differences we have. And this will make some changes in the analysis or calculating the efficiency of the cycle. But let's get back to the TS diagram. So what is happening here? Here we have the point number 6. If we assume the original cycle, if we have this is the outlet boiler, and this outlet boiler we have expansion here at this point. Let's call it 6 star. So compare point number 6 and 6 star. Which one has more vapor? Which one is close to the single phase? Point number 6. So with this reheat, we have expansion happening inside the turbine, okay, and we got point number 6, which is very close to the saturated vapor. So this is one advantage, okay, and we obtain this without any change in the temperature. Let's assume if I don't have the reheat and I need to reach the same point number 6. So what I will do, I will have this reboiler or this boiler. I will continue increase until I have this point. Let's call it 3 star, for example. From point 3 star, I will have expansion to get to point number 6. You can reach point number 6 by 2 ways, with the reheat or without reheat, but superheat the boiler outlet to point 3 star. Compare 3 star and 3. Which one has higher temperature? 3 star. So this means we need special material of construction. So this reheat like solve 2 problems that we can have in Rankine cycle. It gives you like more efficiency. It makes the phase of the outlet of the turbine very close to the single phase, very close to the vapor, without superheating the boiler outlet. So we don't need any material or special material of construction for this boiler. Okay, just with simple idea that we have here. Clear? Okay. So in order to calculate the efficiency we have, the same equations we can use. The efficiency of the ideal Rankine cycle, it's net work divided by Qin. 1 minus Q out divided by Qin. Same equations, but calculating Qin, calculating work, calculating Q out will be different. So this will be the way of calculating Qin. If you need to calculate Qin, now we have 2 steps because we have 2 heating steps happening. We have heating, primary heating happening in the boiler from point number 2 to point number 3. So this is why here we have enthalpy 3 minus enthalpy 2. Then we have reheat happening. So we have here reheat, which is represented by this line, point number 4, point number 5. So H5 minus H4. So we have 2 steps for heating, so you need to calculate each one of them, enthalpy change for each step, and the summation will be Qin. This is Qin that we will use in the thermal efficiency equation. The outlet of the turbine, again, how many turbines we have here? 2. So the outlet of the turbine should be the summation of the work obtained from first turbine plus second turbine. So we have work of turbine number 1 plus work of turbine number 2. Turbine number 1, this comes from this step, 3 and 4. So this is why it's H3 minus H4. Second turbine, it's 5 and 6. So this is why it's H5 minus H6. Clear? So this is the only change we have in the analysis. Q out will not be different because Q out will be in the condenser and Q out will be, anyone can know if we need to calculate Q out? So which H that we will have? What is the line or the state change that represent the condenser? Is it 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 1? 6, 1. So Q out, this will be enthalpy at point number 6 minus enthalpy at point number 1. Because this is the line representing the condenser. Clear? So just, if you can do this, then any one of them, calculate Q in, Q out work of the turbine, any two of these three quantities, use them, substitute in thermal efficiency, and then you can calculate thermal efficiency of the cycle.